In this section, we're going to talk about sequences and series. We'll begin with sequences, and we will write terms of a sequence from the nth term. We'll begin with a finite sequence, and that's a function whose domain is the set of the first n positive integers. An infinite sequence, however, is a function whose domain is the set of positive integers. So there's infinitely many terms. The terms of a sequence are denoted by the letter A with a subscript representing the term number. So as you can see, this A sub 1 is term 1. That's term 3, and so forth. And this is the nth term. Okay, let's see what this is all about. Let's write the first four terms, so first four terms of the sequence defined by the nth term. So they have defined our sequence as a sub n equals n squared plus 5. So we would have a sub 1, here you can see n is 1, is 1 squared plus 5, and we would come up with 6. A sub 2 is going to be 2 squared, because n is 2, plus 5, and we come up with 9. A sub 3 is equal to 3 squared, plus 5, and that's equal to 14. And since we want the first four terms, we'll go to a sub 4, which is 4 squared, plus 5, and that's equal to 21. You can see the terms here, 6, when n is 1. So here we have n here as the x-axis, and we have a sub n as the y-axis. And you can see that we have 6, 9, 14, and 21. And now, from this sequence, we have a function. And so this is the sequence definition. And here is the function. That looks very similar. So we have the second example. And real quick, this sequence depends on n, and this function depends on x. And you can see that's right where that x is found. Okay, let's go ahead and try number 2. Number 2, we have a sub n equals 3 multiplied by negative 1/3 raised to the nth power. And here we want the first four terms of the sequence. So a sub 1 is equal to 3 multiplied by negative 1/3 to the first power, and that equals negative 1. A sub 2, now n is 2, 3 multiplied by negative 1/3 squared, and that's going to be equal to a positive 1/3. A sub 3, 3 multiplied by negative 1/3 cubed, we're going to have a negative 1/9 if we multiply that out. And finally, a sub 4, 3 multiplied by negative 1/3 to the fourth power, and we have 1/27. Okay, now notice that the terms of the sequence 2 alternate in sign. As you can see, positive here, and that's negative, and that's positive. Oops. I'll write that here. Here we have a negative term and a positive term and a negative term and a positive term, and these alternate in sign. When you have a sequence that alternates in sign, you have what we call an alternating sequence. And the alternation in signs can be represented in the nth term by a factor of -1 raised to a variable power. So a factor of -1 raised to a variable power. And what that will do is that will alternate between an even and an odd integer. For example, if you have a sub n equals -1 raised to the nth power, here all of your odd numbered terms are going to be negative and your even number terms are going to be positive. Let me give you an example. A sub 6 is going to have -1 to the 6th power and whatever else. And that's going to be equal to 1 times all of these. So that's going to be positive. Okay, so that's what they mean by that. However, you could also write this as -1 raised to the n plus 1. And you can have also -1 raised to the n minus 1. And here, your odd numbered terms will be positive and your even numbered terms will be negative. An example of that would be a sub 6 equals -1 to the 6 plus 1. That's -1 to the 7th power, and that's actually equal to -1. So that's negative. So it just depends on which factor of -1 you raise it to. Okay, now we're going to talk about something called recursiveness and a recursive formula. Here we will be writing terms of a sequence defined recursively. And a recursion formula defines the nth term of a sequence as a function of one or more terms preceding it. So it defines this sequence as a function of a preceding term. Okay? So let's take a look at this number 3. Write the first 4 terms. So we need the first 4 terms of the sequence defined by a sub 1 equals 3 and a sub n equals 4 multiplied by a sub n minus 1 minus 2. So let's just try this. If a sub 1 is equal to 3, a sub 2 is equal, now we're following this formula right here. A sub 2 is equal to 4 multiplied by a sub 1 minus 2. And that's equal to 4 times 3 minus 2. And that's equal to 10. Let's try a sub 3. A sub 3 is equal to 4 multiplied by a sub 2. As you can see, we want the previous sequence term there. So 4a sub 2 minus 2, and we have 4 times 10 minus 2, and we come up with 38. Likewise, a sub 4 is 4 multiplied by a sub 3 minus 2. That's 4 times 38 minus 2, and we come up with 150. Okay, let's talk about this beautiful sequence called the Fibonacci sequence. And the Fibonacci sequence is given as the first term is 1 and the second term is 1. And then every next term, all of the n terms, are the n minus 2 and the n minus 1 terms added together. So the first 2 terms, the very first 2 terms of the Fibonacci sequence are 1. And then after that, they add the previous 2 numbers together. So there's your first, there's your second. And here 2 is 1 plus 1. Let me circle this in a different color. 3 is 1 plus 2. 5 is 2 plus 3, and so forth. So that's the Fibonacci sequence. Now we want to introduce something called factorial notation. And factorial notation is really important, and it is used, and it's actually an exclamation point written after a number. So here you have n factorial. So n is a positive integer, and the expression n factorial takes n, so this number here, and multiplies it by the previous integer and the previous integer until you get all the way down to 2 and 1. And if you have n equal to 0, we do define 0 factorial as 1. So both 0 factorial is 1 and 1 factorial is equal to 1. So you will need to know both of those. Let's go ahead and try one. 5 factorial. So we're going to take 5 and we're going to start multiplying every number below it until we reach 1. And if you multiplied those together, you'd get 120. Looking at number 5, take a look at this. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And then 4 factorial is 4 times 3 times 2 times 1. And what do you notice? We can cancel those out, and we simply have 30. Okay, using that fact, let's take a look here. 9 factorial is 9 times 8 times 7 times 6 times 5 factorial. And you'll see why I stopped at 5 factorial, because 4 factorial is 4 times 3 times 2 times 1 times this 5 factorial. And these 5 factorials cancel. And if you work this out, you can also see 4 times 2 is 8. So we end up with, well, you can do the math there. But anyway, I came up with 126. But you could actually start canceling, 6 divided by 3 is a 2. You could start doing things like that. Or I would just use your calculator. Okay, number 7, we come up with n factorial is n multiplied by n minus 1. Oh, well, that's n minus 1 factorial divided by n minus 1 factorial. So what you notice here is that n factorial divided by n minus 1 factorial is just n. Okay, let's take a look at a sequence defined with a factorial in it. Here in number 8, you can see that the sequence is defined by a sub n equals 3n factorial divided by n cubed. And they'd like us to find a sub 3. So you can see here that a sub 3 is, and here n is 3. Put that there. And then here we're going to have 3 times 3 factorial divided by 3 cubed. And we'll just take this one step at a time. That's 9 factorial divided by 27. And that's equal to 362,880, if you work that out, divided by 27. And I came up with 13,440. So that would be the third term of that sequence. Okay, now we'll begin with something we call summation notation. So let's take a look at this. The sum S of the infinite sequence. So as you can see, it's an infinite sequence because we just have dot, dot, dot. It's just going to go on and on and on. Is called an infinite series and is represented by S equals A sub 1 plus A sub 2 plus A sub 3 and so forth. So the sum of the first n terms of a sequence is called the nth partial sum. And it is denoted by S sub n. So the nth partial sum of a sequence is a finite series. And here we have a Greek letter sigma that looks like this. I usually would draw mine like that. And it's used to represent summations. Okay, so let's take a close look at this. N is the upper limit, 1 is the lower limit, I is the index. It's changing each time. I is 1, 2, 3, 4, 5, 6, all the way until you get to N. And as you can see, this is your sum all the way up to that nth term. The sum of all terms in the sequence is an infinite series, and that infinite series is given by this expression, and you can see the infinity there at the top of the sigma notation. So let's see what we have. I think it's easier to use it than to define it. Here we're going to write the terms for each series and then find the sum. So here we want to go ahead and have 3 times 1 minus 8. And now remember, this sigma notation is summation plus, and we started with 1 and we'll have to go to 3. So we have 3 times 2 minus 8, and then we'll add that to 3 times 3 minus 8. And when we put all that together, we get negative 5 minus 2 plus 1, and we come up with negative 6. Okay. If I can make that a little bit smaller. Okay, let's take a look at number 10. In number 10, we're going to start with I equal to 1. So our first term will be 2 times 1 divided by 1 squared. Now we'll move on to I equal to 2. So here we have 2 times 2 divided by 2 squared. 2 times 3 divided by 3 squared. And now finally we're at I equal to 4, which is 2 times 4 divided by 4 squared. And you can put that in your calculator if you'd like, or check this. And I came up with 25/6. Okay. Okay, now we have J starting at 3 and going to 5. So we'll just follow along -1. So we first have J is equal to 3. So this is J plus 1, which is 4, and 3 times 3. So we'll just take our time with this. Now we have -1 to the 5th power multiplied by 3 times 4. And then we have -1 to the 6th power multiplied by 3 times 5. And I got 12. So this is a real interesting summation notation. We have n from 1 n equal 1 to 4. However, there is no n to substitute for. So when n is 1, we have 10. When n is 2, we have 10, 3, and 4. So we really have n 4 times, and that's equal to 40. Okay, note that the same sum may be written in many different ways. So as you can see here, we have I starting at 1 and going to 4. Let's see what we have. So we have 1 squared plus 2 squared plus 3 squared plus 4 squared. Now, what if we started at 0 and went to 3? And here we would have 0 plus 1 squared, 0 plus 2 squared, 0 plus, let me move that down, 3 squared. Oh, excuse me, I did that wrong. Let me start over. J is in the front. So that would be 0, 1, 2, and then we need our 3. Whoops, goodness gracious. There we go. So J started at 0 and went all the way to 3. And so we have 1 squared plus 2 squared plus 3 squared plus 4 squared. So you can see that's the same. And let's take a look at this last one. So the same sum may be written in many different ways. So here we have, starting at k equal to 2. So we have 2 minus 1 squared plus 3 minus 1 squared plus 4 minus 1 squared plus 5 minus 1 squared. And again, you can see we have 1 squared plus 2 squared plus 3 squared plus 4 squared. So 3 different ways here to come up with the same sum. Okay, now let's go the other way. Let's look at these series and these sums and see if we can go the other way. So as you can notice, let's take a look at the numerator. The numerator is 2 to the first, 2 to the second, 2 cubed, and so forth. So it looks like we might have a 2 to the n in the numerator. And that n would have to start at 1 because of this 1. So we'll start at 1. And then let's look at the denominator. The denominator is always 5. So we'll place 5 in that denominator. When did we stop? This is 2 cubed, 2 to the 4th, and that looks like, and I'll go ahead and we don't have to write all of them normally, but so as you can see, we will stop at 5. So that is why we will write a 5 here. Okay? Okay, let's look at number 14. As you can see, we have a 2 in the denominator when we begin. And it's kind of interesting because here I can see this 8 is a 2 cubed, and this 4 is a 2 squared, and here we have 2 to the first, and anything to the 0 power is 1. So what do you notice? This must be 2 to the negative 1. So let's see what we can do. We're going to have the sum, and we're going to start with n equal to 1. We have to. So how can we get this negative 1 here? from a 1, what we would have to do is we would have to say 2n minus 2, and that would give us a negative 1. So here we need n minus 2 to equal a 3 right here. So n would end at 5. Now, taking a look at that, you could also write it with n equal to 1 beginning and going to 5, and you could have 2 to the n divided by 4. I'll let you check this, but this is just another way. But I do like this one here, just following along. Okay, let's take a look at number 15. As you can see, we have both 2 and 3. So it looks like we have 2/3 to the first power, and then we have 2/3 squared, and we have 2/3 cubed, and we have 2/3 to the fourth power. Now, we are changing sign, negative, positive, negative, positive. So here, we're going to have a negative 1 raised to the nth power in order to have that alternate. So let's see if we can write that. We can say that this is equal to the sum, n equal 1 to 4, and we will have negative 1 to the n multiplied by 2/3 to the nth power. Move that down. Now, you could also bring that negative 1 in those parentheses and have a negative 2/3 to the n. So you could do that. I prefer this. Okay, let's look at some properties of summation. And these properties are quite interesting, and this is where we will end this section. This coefficient here, you can add a constant c a total of n times equal, and that will equal Cn. And so a constant can also be factored out of a summation, and a single sum or difference can be regrouped as two sums or two differences. So this constant can go on the outside of the summation notation. If you just have a constant here, you can multiply that constant by n. So adding a constant n times equals c times n. And then breaking up this plus and minus, and each sum having its own sigma notation. And that concludes this section.